Today, total productive maintenance, or TPM, is helping many companies increase their output by improving the efficiency of their equipment and their maintenance organizations. TPM increases output by optimizing production, quality, cost, delivery, health and plant safety, and employee morale. For example, equipment failures and process errors fell sharply at a Matsushita electric plant after TPM was adopted there in 1978. At the same time, productivity, overall output, and output per worker rose dramatically. Similar results were obtained at Tokyo Car Corporation. When TPM was introduced to boost profitability, output capacity increased significantly over a 4-year period. The percentage of products meeting quality criteria also increased. Moreover, in the first 5 years, machine improvements implemented through TPM saved the company $8.6 million. Here's another example. A TPM program aimed at improving efficiency at steel products manufacturer Topi Industries. As this graph shows, production equipment efficiency rose significantly. For example, this chart shows an 80% reduction in the number of workdays lost due to downtime per 1,000 machine hours. Topi's defect rate also dropped dramatically. These are just a few examples of improvements achieved through TPM. This program will show you how TPM can generate similar results at your company or plant. As automation and labor-saving equipment take production tasks away from human workers, the condition of production equipment increasingly affects output, quality, cost, delivery, health and safety, and employee morale. In any plant, many kinds of equipment must be maintained. Problems occur often, and many different factors must be considered in solving them. As workers are replaced by machines, however, they become less concerned about machine problems. Seeing themselves merely as operators, they are less likely to detect abnormalities in equipment operation. Maintenance personnel, on the other hand, typically assume that a machine that's running must be in good condition. They spend most of their time treating sporadic breakdowns, unexpected dramatic failures. They are likely to ignore chronic failures, less obvious defects in operating conditions that contribute to gradual deterioration in machine performance. When workers understand their true role in production, however, they can begin to eliminate waste and losses by restoring equipment and maintaining it in top condition. People still control production, no matter how thoroughly it is automated, no matter how many robots are used. Even when a company shifts completely to automated production, human maintenance personnel and operators must still maintain equipment and determine what tasks it will perform. In reality, all equipment phenomena, whether good or bad, can be traced back to some human act or omission. The success of production depends entirely upon us. When we understand that people control production, we start to see equipment from a fresh perspective. We become more interested in improving it. We understand why it is so important to build quality into equipment. We prevent manufacturing and quality problems by setting and maintaining appropriate standards for equipment and tools. TPM changes how people think about equipment, and it involves everyone, from top management to operators, in achieving and maintaining optimal equipment operating conditions. TPM has 3 goals: to maximize the operating efficiency of each piece of equipment, to provide comprehensive maintenance spanning the equipment's life cycle, and to accomplish this through the active cooperation of engineering, operations, and maintenance departments. That is, everyone who plans, designs, uses, or maintains equipment. TPM promotes this cooperative effort by involving everyone from top management to the production line in what we call motivation management. All plant maintenance activities are planned and implemented by small groups at each level. As this figure shows, TPM is built on thorough productive maintenance, which adds maintenance prevention and maintainability improvement to conventional PM activities. TPM is unique, however, in its use of autonomous maintenance, or operator maintenance, as well as small group activities to achieve these goals. With this unique approach, TPM overcomes traditional divisions and unites operations, maintenance, and engineering personnel in a company-wide effort to promote effective maintenance. The goal of TPM is to maximize output, to increase the productivity of plant and equipment. This means improving productive capacity, quality, cost, delivery, workplace safety and health, and worker morale. This is accomplished by minimizing input. Our goal in improving and maintaining equipment at optimal levels is to reduce its life cycle cost. In other words, to optimize overall efficiency or cost effectiveness. TPM improvement activities seek to reduce life cycle costs by eliminating the 6 big equipment losses. The 6 big losses include equipment failure, delays due to setup and adjustment operations, idling and minor stoppages caused, for example, by misoperation of sensors or work blockages on chutes, reduced speed, or the difference between actual and design speeds, process defects, and reduced yield from startup to stable production. TPM activities aim to reduce these losses to zero, to restore plant and equipment to their ideal conditions, and to maintain them at that level continuously. To address the 6 big equipment losses, TPM offers 5 fundamental improvement activities. First, systematically improving the effectiveness of individual pieces of equipment. Second, establishing an autonomous maintenance program for operators. Third, setting up a planned or scheduled maintenance program in the maintenance department. Fourth, improving operating and maintenance skills through technical training. And fifth, an early equipment management program starting at the design stage to assure optimal performance and economic lifecycle costs. These activities are implemented over time as part of a TPM development program. Let's review each activity in more detail. Project teams made up of production engineers, maintenance staff, and line foremen initiate equipment improvement activity by selecting bottleneck processes to serve as model projects. Each team chooses an improvement focus related to one of the 6 big losses: breakdowns, setup and adjustment, idling and minor stoppages, reduced speed, process defects, or reduced yield. Several project teams, each focusing on different types of loss, develop improvements simultaneously and share their results with the other teams. Small group activities based in each functional area then continue the work of improving every piece of equipment. In carrying out equipment improvements in your plant, remember to select a focus for improvement that reduces one of the 6 big losses. While the object of individual equipment improvement is eliminating losses, the goal of this first TPM activity is changing the way people think about plant and equipment. Chronic loss is an important focus in equipment improvement activity. These regularly occurring problems are often neglected after repeated attempts to eliminate them have failed. Chronic problems do not improve for several reasons. Sometimes a problem is inadequately investigated and analyzed. In other cases, the wrong cause is identified, or a significant cause is treated, but another contributing factor is overlooked. Typically, more than one cause is involved in the occurrence of a chronic problem, and the principal causes are changing constantly. The severity of the loss also varies depending on the importance of the causes contributing to it. For these reasons, we need patience and an innovative approach in tackling chronic problems. To eliminate a chronic problem, we begin by gaining a thorough understanding of its nature and causes. We study the phenomenon as it occurs and examine every factor related to it. Conducting a comprehensive physical analysis of the chronic problem forces us to consider factors we might otherwise overlook. We call this thorough study of problems PM analysis. Through PM analysis, we identify defective conditions among the causes related to the problem and eliminate them one by one. This approach steadily reduces the chronic problem and often leads us to its solution. When we take steps to prevent every slight defect or defective condition associated with a chronic problem, we stop the endless cycle of repair and defect recurrence. Now, let's look at some examples of equipment improvement. Our first example is from the Zero Defects, Zero Adjustments campaign at Naki Fujikoshi Corporation, a leading Japanese manufacturer of bearings and industrial robots. In this process, the grinding precision of the external cylindrical grinder determines whether the finished product will have the correct dimensions. Through PM analysis, the performance of the grinder was improved so that it now produces zero defects. As the grinder ground the material, grinding defects occurred as the result of deviations from the ideal parallel orientation of the grinding wheel and the material being worked. These defective conditions caused the grinding wheel to cut the material too deeply or too superficially, and resulted in a finished product with incorrect dimensions. To solve the problem, the team first conducted a PM analysis. Let's take a look at this table, which documents a portion of their work. Notice that in the first two columns, the team describes the nature of the defect and its immediate physical cause. In the third column, they identify various factors that might produce the defective condition. Then, in the next two columns, they analyze those factors in terms of their relationship to other factors, equipment, tools, material, and so on. For example, here they have noted 5 possible causes related to the center: use of a defective part or the wrong part, faulty insertion, precision of the manufacturing method, and possible collision with the grinding wheel. They also studied causes related to equipment precision and operator error. The direct cause of the problem was play in the bearing used to rotate the table. A spring was attached on the grindstone side to prevent this problem during rotation. Here is the spring that was installed. Other improvements to the machine increased its precision as shown. The defect rate fell from 4 or 5% to 0. With the increase in precision, deviations in the dimensions of the finished product vanished. In this process, the end mill groove grinding team reduced setup adjustments significantly and achieved a 100% acceptance rate. Eliminating frequent setup adjustments increased productive capacity from 400 to 500 units daily. This process grinds grooves in material to produce end mills. After the production run, adjustments involved in setting up for the next product, including measurements, took 68 minutes and 30 seconds. Moreover, 5 trial products produced during the adjustment operations had to be scrapped. At this point, improvement activity aimed at reducing defects to 0 had just begun. Notice on this table that standard values had not been established for 2/3 of the adjustment items. These standard values were established by asking why each adjustment was needed and by reviewing the way in which it was carried out. Measuring devices were installed at each adjustment point, so standard values could be controlled each time the setup was performed. These improvements reduced the setup from over an hour to 9 minutes. Now, acceptable products can be produced immediately without trial processing. The following example is from the Zero Defects, Zero Minor Stoppages campaign at Daihatsu Motor Company, a Toyota Group manufacturer of compact cars and commercial vehicles. Zero defects was achieved in this process through improvements to the inner die clamp SC pump. This pump was experiencing 7 or 8 failures per month. Because the design specifications manual was unavailable, maintenance personnel were having difficulty finding ways to prevent the failures. Using PM analysis, the improvement team studied the physical characteristics of the pump failure and the conditions that produced it. Then they developed and implemented solutions for each cause of failure. Moreover, the team arranged for the in-house preparation of a new equipment specifications manual, which was used to inspect and maintain the pump at optimal conditions. As a result of this improvement activity, pump failures fell from an average of 7 or 8 times per month to 0. Another team in Daihatsu Motor's sheet metal process tackled the problem of minor stoppages. In this continuous flow process from sheet metal to finished product, speed losses directly affected the number of units produced. As soon as the project was organized, team members began observing the problem continuously to better understand it. They discovered that stoppages estimated at 4 to 5 per week actually occurred 15 or more times per week. Astonished at how frequently the stoppages occurred, the team conducted a PM analysis and implemented a variety of improvements, just a few of which are shown here. Notice again how the team began with a description of each stoppage and its apparent physical circumstances in the first 2 columns. Then they reviewed all the possible reasons for the phenomena and developed solutions in the next 3 columns. As a result of the team's efforts, the frequency of minor stoppages declined sharply. As these examples show, you can always achieve more than the result you aimed for in TPM improvement activity. Teams discover many opportunities for improvement when they investigate a problem thoroughly with open minds. Let's review the principles of equipment improvement. The causes of a chronic loss can be difficult to identify. They have many causes, and a different cause may be involved in each occurrence. Furthermore, their occurrence depends on complex factors. Multiple causes are involved, and their relationship to each other and to the problem changes constantly. Therefore, to succeed in our improvement activities, we must understand the problem in question, thoroughly analyze its physical characteristics, study all related factors, and then eliminate the defective conditions associated with each of these factors. Basically then, implementing improvements involves 2 steps. First, we analyze the phenomenon correctly by reviewing all related factors. PM analysis helps us understand the problem by forcing us to look carefully at its chain of causation. Second, we eliminate defective conditions associated with the problem and stop the endless cycle of repair and defect recurrence. Remember, the only sure way to eliminate chronic losses is to systematically eliminate, one by one, all defective conditions, even those that at first appear unrelated to the problem you're investigating.